Microfluidic flow control is crucial for precisely manipulating tiny amounts of fluids in lab-on-a-chip devices, biosensors, and chemical reactors. Unlike traditional fluid systems, microfluidics operates under low Reynolds number conditions, meaning fluid motion is dominated by viscous forces rather than inertia. To move and control fluids, different forces and gradients are used. To move and control fluids, different forces and gradients are used. The pressure-driven flow, such as syringe pumps, is the most common, ensuring steady, predictable movement. Electrokinetic forces, like electrophoresis, moving charged molecules using an electric field, and electroosmosis, pushing neutral fluids via charged walls, allow for highly controlled and valve-free flow. Capillary action enables passive movement, particularly in paper-based microfluidics, where small channels wick liquids without external power. Think of how a tissue absorbs water. Acoustic waves can generate pressure gradients to manipulate droplets and cells with great precision, useful in biological sorting applications. Magnetic fields are employed to steer magnetic nanoparticles, enabling controlled drug delivery or biochemical reactions. Thermal gradients induce flow via Marangoni effects, where surface tension variations move the liquid, much like the motion seen in a heated oil pan. What's the best control method? It depends on the application. Do we need high-speed mixing, precise molecule separation, or completely passive flow? Advances in smart materials and programmable microfluidics could soon allow fluid transport to be controlled dynamically, opening doors for even more sophisticated biomedical and industrial applications. Due to the small dimensions of microfluidic channels, fluid flows predominantly in a laminar regime, meaning there is minimal turbulence, and molecules move in parallel layers. This allows precise control over mixing, diffusion, and transport of chemical or biological samples. The low Reynolds number characteristic of microfluidic flows ensures predictable and stable behavior, which is crucial for applications such as single-cell analysis and controlled chemical reactions. In microfluidic cell culture systems, laminar flow prevents shear stress on cells, enabling controlled nutrient supply and waste removal. Laminar flow in microfluidics is like orderly lanes of highway traffic, where vehicles move smoothly without chaotic interactions. Pressure-driven flow is widely used in microfluidics, where an external pressure source, e.g., syringe pumps, peristaltic pumps, or compressed gas, drives fluids through microchannels. The flow rate depends on the pressure differential, channel dimensions, and fluid viscosity, following the Hagen-Poiseuille equation. While effective, pressure-driven flow may cause variations in velocity due to resistance and channel surface interactions, requiring precise calibration. In lab-on-a-chip devices for blood analysis, pressure-driven flow ensures a consistent sample transport rate for accurate biomarker detection. This system works like water flowing through household plumbing, controlled by the pressure applied at the inlet. Electrokinetic flow exploits the movement of charged particles in response to an applied electric field, including electroosmosis, fluid flow driven by charged channel walls, and electrophoresis, movement of charged molecules. This technique allows precise, valveless fluid control without mechanical pumps, making it ideal for miniaturized and automated bioanalytical systems. However, electrokinetic effects are highly dependent on buffer composition, pH, and surface charge properties. DNA separation in microfluidic electrophoresis devices uses electrokinetic forces to precisely move and sort biomolecules based on charge and size. It works like ink spreading in an electrically charged printer, where the movement is dictated by an applied voltage. Capillary action enables fluid transport in microchannels without the need for external forces, relying on the interaction between liquid molecules and channel walls. The movement depends on the balance between adhesive and cohesive forces, which can be engineered by modifying surface wettability. Capillary-driven flow is essential for paper-based microfluidic devices and diagnostic assays, particularly in low window settings where external power is unavailable. Lateral flow test strips, such as pregnancy tests, use capillary action to transport fluids and detect analytes. This process is similar to how a sponge absorbs water, pulling liquid through tiny pores. Acoustic waves generate localized pressure gradients that induce microfluidic streaming, enabling precise manipulation of fluids and particles. This technique, often achieved using surface acoustic waves, SAWs, allows non-contact control over droplet movement, mixing, and particle sorting. Acoustic microfluidics is particularly useful for applications requiring gentle handling of biological samples, such as cell separation and drug screening. Acoustic tweezers use sound waves to trap and position cells in microfluidic systems for single-cell studies. Acoustic streaming is like using ultrasonic cleaning, where sound waves create microcurrents that move tiny particles efficiently. Magnetic microfluidics leverages external magnetic fields to manipulate magnetic nanoparticles, ferrofluids, or magnetically tagged biomolecules within microchannels. This enables controlled transport, mixing, and separation without physical contact, reducing contamination risks. Magnetic forces are particularly useful for point-of-care diagnostics and lab-on-a-chip applications involving biomolecule sorting and pathogen detection. Magnetic beads, functionalized with antibodies, can be used to isolate specific proteins from blood samples in diagnostic devices. Magnetic fluid control is like a magnetic stirrer in a laboratory flask, mixing substances without direct mechanical contact. Temperature variations create localized changes in fluid density and surface tension, driving flow through thermocapillary and thermophoretic effects. These mechanisms allow controlled fluid motion and molecule transport without mechanical pumps, making them useful in heat-sensitive biochemical assays and DNA amplification techniques, such as polymerase chain reaction, PCR. However, precise temperature control is necessary to avoid unwanted convection currents. Thermal microfluidics is used in PCR chips, where controlled heating and cooling cycles enable rapid DNA amplification. This process is like the rising motion of hot air in a chimney, where temperature differences drive movement. Chemical gradients drive diffusive and convective transport in microfluidic systems, allowing for precise control of reaction kinetics and cellular responses. This is particularly important in chemotaxis studies, where cells migrate in response to concentration gradients of signaling molecules. Chemical diffusion can be engineered by microchannel geometry and flow rates to create stable gradient profiles for controlled experiments. Microfluidic gradient generators are used to study how cancer cells respond to different drug concentrations. Chemical gradients in microfluidics work like scent dispersing in a room, with molecules spreading from a high to a low concentration area. Many advanced microfluidic systems integrate multiple flow control mechanisms, such as combining pressure-driven flow with electrokinetic effects or acoustic streaming with magnetic forces. These hybrid approaches enable greater flexibility, precision, and efficiency in fluid handling for high-throughput screening, organ-on-a-chip models, and bioanalytical applications. The integration of artificial intelligence and automation further enhances performance, enabling adaptive control of fluid dynamics. In digital microfluidics, a combination of electrokinetic and magnetic forces is used to move, mix, and split droplets for lab-on-a-chip applications. Hybrid microfluidic control is like an orchestra where multiple instruments work in harmony to achieve a complex and precise performance.